This shows the what we would call power factor corrected version, and I don't think the neon's showing on the display. It's coming back on again. That's the synchrony effect of the camera taking the picture and whether the neon's actually glowing. To our eyesight, it's glowing continuously. Now, when the system was first made, it was made using just the two central coils, and without the presence of the secondary coils. In this case, we got 299 volts, enabling 9.78 milliamps through that neon discharge. And we'll leave that neon discharge there again. See if we can pick up sort of cycle time, when we can see it, when we can't. See if it phases out. It's phasing out. Should begin phasing in pretty soon. So we got these long cycle times of between when the cameras are taking a picture and when it's taking a picture that neon discharge actually isn't occurring. So that's what I'm seeing that for. There goes the cat disturbing the camera. Okay. Then over here, what we did to power factor correct it is we added another cap to the system so that it would compensate for the loss of inductive reactance brought on by bringing in the secondary loops into those poles' vicinity. So if we went and tested the matching of the reactances, which would be hard to do with the neon because it's got to be lit for it to be tested against, where a night light you can get away with it, but not neon. But in any case, we have much better results, and the neon ignites at 15.3 volts. We're bearing 4 amps on that primary, and it's hard to say. We might still be slightly inductive on our primary agreements. We just wanted to verify that we now have made power factor corrected adjustment on this device, and it has increased its efficiency quite a bit, I would say. But with that increase of efficiency, of course, comes the lower level that we're exploiting. We have the time lag of the camera seeing that neon, and I think what we'll do to finish out is turn that up to a little bit of a higher level. And here's the scoping of the resonant voltage rise. Versus the time periods. And it looks like it might be a little bit not, well, it still looks like about 90 degrees, maybe a little different. Well, we'll go back over here. Focus on this and go up to a higher operating level and see what we can get with the higher operating level. We're at 9.59 milliamps. Don't expect the voltage to change much. 299 volts. Oh, kicked it out. We're at 26 volts. I kicked it out at 30 volts from the variac. We're now at 26 volts input. Well, 21.7 at 6.10 amps. The voltage went down on the input. Variac says 26. Now we got about 30 milliamps for making comparisons of all the efficiency drops in this system. And let's see if we can see a cycle effect on that and close it out. Cycled out, cycled in. Looks like we might have a quicker cycle in and out with this bulb, this intensity. Cycling out, cycling back in. Okay, I think that'll be it. Call for this video. We'll let it cycle one more time. Call it quits. Certainly a long period of on-offs between. That's it.